Rockets have a limited size. You can only put a certain amount of propellants on board. And so there's a real question of how much performance can you get out of a given amount of propellant that you can load on board. And this is where we get into a little bit of mathematics. If you don't want to follow the math, you can skip ahead a little bit, but the conclusions of this section are really critical. So even if you don't want to follow the math, please do come back and join us when we get to the conclusions, because this famous rocket equation, which we're going to derive and then show how it's used, is really critical in answering some of the questions about why spaceflight is so difficult. Why is it so hard to get into space? It takes a lot of energy to get up there. How much energy do you actually need to put 1 kilogram in orbit? Well, if you remember your high school physics, there's two forms the energy can take. There's potential energy that you need to actually raise 1 kilogram off the surface of the Earth. And let's say we're going to about 400 kilometers, okay? And we're going to neglect the fact that the Earth's gravity is an inverse square law and the gravity gets slightly weaker as you go away. But let's just assume that it's 9.8 meters per second squared, which is what it is here on the surface of the Earth. So if we take 1 kilogram, the potential energy that you need to raise it a certain distance is the mass times the gravitational acceleration times the height, mgh, and we work out the numbers here. 1 kilogram, 9.8 meters per second, 400,000 meters. We're using the MKS system, and we get about 3.9 megajoules of energy. Now, the other energy that we need is the kinetic energy, because if you just put something 400 kilometers up in the air and let go of it, it's going to fall back down to the Earth. We'll see later in another lecture about orbital mechanics that in order to stay in orbit, you need to be going at a rather high speed. In fact, just about 8 kilometers a second to be in orbit a few hundred kilometers above the surface of the Earth. And we know from high school physics that kinetic energy is 1/2 the mass times the velocity squared. So we take the mass of 1 kilogram, we square the velocity of 8 kilometers per second, and we get 3.2 times 10 to the 7th joules, or 32 megajoules. So we can see in low Earth orbit, the kinetic energy dominates over the potential energy, but let's add them up together and we get 36 megajoules. Now we're going to convert the energy, because 1 joule per second equals a watt, so 1 joule equals 1 watt second, and 36 megajoules equals 3.6 times 10 to the 7th watt seconds. And we can convert that into kilowatt hours, which is the units that we use to measure electrical energy consumption. Typically, I pay maybe a little more than 10 cents a kilowatt hour. So 10 kilowatt hours, that costs about $1. That's the amount of energy that it takes to get 1 kilogram into orbit. And I hope you find that surprising, because the amount of energy, if we could just put that energy right into that 1 kilogram, is really very inexpensive. It would revolutionize the space business if we could do that. But of course, we have to use rockets to get into space. And the propellant that you need for that last little bit of your acceleration up to orbital velocity, you had to carry all the way with you. So you needed propellant to carry the propellant that you're going to use, and then you need more propellant to carry that. And the whole thing is kind of an exponential runaway, and that's what we're going to look at when we deal with the rocket equation. So this is kind of a surprising result for most people. It really shows what we sometimes refer to as the curse of the rocket equation, because that's what we have to deal with. We can't get 1 kilogram to orbit for the cost of $1. It does cost many thousands of dollars. We can do much better. So let's take a look at the rocket equation. Let's look at a schematic of a simple rocket. And as we saw before, we have the propellants, we have the fuel, we have the oxidizer, together, those are the propellant, and we can talk about the mass of the propellant. Of course, the reason we're launching the rocket is we have a payload which we want to put into orbit, so we have the mass of the payload. But then the rocket itself has a certain amount of mass. The structure, the skin around the outside of the rocket, the fins, the mass of the rocket motor itself, and so on. All that is the structure of the rocket, and we lump that together as the structural mass. And so when you have a fully loaded rocket sitting on the launch pad, we have what we call the initial mass of the rocket, which is the mass of the payload, plus the mass of the structure, plus the mass of the propellant. And we'll see later that for typical rockets, the mass of the propellant is completely dominant. So now we fire the rocket engine, and for simplicity now, let's assume that we're out in free space, so we don't have to worry about atmospheric drag, we don't have to worry about gravity. There's no force acting on the rocket except the force of the rocket engine itself. If we want to calculate the thrust, that is the force, what we're really looking at is, remember we have all of the gas that's now being directed out the backside, and we take the amount of material that's coming out, that's the mass flow rate, the time derivative of the mass, times the velocity at the exit, or the exhaust velocity, we call it, V sub E. And that will give you, by conservation of momentum, that gives you the forward thrust. Now there's another term here that has to do with the pressure, which we're going to ignore for now. Let's just assume we're flying in a vacuum. So basically this is the equation we're going to work with. The forward thrust of the rocket equals the rate at which the mass is flowing out of the rocket, that is the rate of the mass of the exhaust times the exhaust velocity. And by conservation of momentum, we'll get forward motion of the rocket. All right, so let's take the rocket on the launch pad, and we showed the initial mass. Now we're in free space, we look at the rocket, and what's the difference? It's now still has its payload, still has its structure, but the propellant tanks are empty. And so the final mass of the rocket is now the initial mass of the rocket minus the mass of the propellant. This is just setting up the basics for calculating how much we can get out of that mass of propellant. The mass of propellant is fixed. It's limited by the size of your rocket and the way you store your propellants. Now let's look at how all these equations fit together. So remember that we looked at the basic force from the conservation of momentum, which equals the mass flow rate times the exhaust velocity. That's the force. But we also know from Sir Isaac Newton that force equals mass times acceleration. Now the mass is changing because you're taking some of the mass and you're throwing it out the back of the engine. M is the instantaneous mass at any given time, and so the force equals the mass times the acceleration, which is the time rate of change of the velocity. And that's the velocity of the rocket now, which is not the same as the velocity of the exhaust, which, when we multiply it by the time derivative of the mass, that is the mass flow rate, also gives us the force. So we have these two expressions for the force, one from the conservation of linear momentum and one from Newton's law. And now we can work with that. You notice we have dt in both denominators. We can get rid of that, and so we're left with an expression of dv on the left side. That's the increment in velocity that you get by burning that little increment of mass, which is the dm. That's the mass which you've just thrown out the back of your engine. And the equation, of course, has the v exhaust, which we can treat as a constant, and dm divided by the current mass on the right-hand side. Now, let's integrate from the initial state to the final state. And again, if you haven't had calculus and you can't follow this, hang in and come back and look at the final conclusion, because it's really quite important. So we're going to integrate from the initial state. In this case, it's the initial velocity to the final velocity. On the other side, it's from the initial mass to the final mass. And of course, the integral of dv is just v. And so we have on the left-hand side the final velocity minus the initial velocity, which we call the change in velocity. And delta is the Greek symbol we use for change, so we often refer to this as the delta V, or the velocity increment that we can get by burning a certain amount of propellant. And on the right side, the integral of dm over m is just the natural log of m, and so we put in the numbers and we get the log of the final divided by the initial mass. We have a minus sign because the exhaust velocity is going in this direction, but the velocity of the spaceship is increasing in this direction. And so we can get rid of the minus sign and just flip the numerator and denominator in the logarithm. And we now have essentially the rocket equation. The amount of change in velocity that you can get by burning a certain amount of fuel is equal to the exhaust velocity of that fuel coming out the back of the rocket times the natural log of the ratio between the initial mass that's with the propellant and the final mass when you've burned that propellant. And so for a given amount of propellant, this rocket equation essentially tells you how much you can increase the velocity of your rocket, or decrease if you want to slow down.